Sound check. Good to go. All right, I think we're ready to begin. Welcome again, everyone. So let's jump right in. First, a few slides just covering the whole progression of the course. I think the course is structured into modules, designed so that you can take independent modules depending on your background, depending on your interest. I believe everyone in this course is sitting in for the whole course, which is great. Might help us streamline things a little bit. So 4 modules. The first module starts from basic logic gates. What is digital logic? What are CPUs? So we'll play around with digital logic concepts and CPU concepts in the first 2 days. Days 3 through 5. And again, since everybody is taking the whole progression, if we need to make adjustments to the timetable, that's perfectly fine. We've got plenty of room at the end for final projects. We can stretch this out a little bit if that makes sense, or even pull it forward. I think probably we might stretch it out, but we'll see. So days 3 through 5 is where I think the exciting aspects of the course come into play, where you design a RISC-V core from scratch. Day 6. We'll step back. So most of the content for this entire 2 weeks, or at least the first week, is all hands-on, short little lecture, labs, hands-on labs. Everybody's got their laptops with them, I hope. You'll be using them a lot. But day 6 is more lecture. So we'll talk about how all this fits into context. How does a design team operate? What are the different roles involved in the design team? And then days 7 through 10 is all about your final projects. So based on the skills that you've learned, you'll have time to apply those freely any way you want. It's a completely open-ended project, targeting tiny tape-out, which we'll talk about more, but that's a path to actually fabricating your designs in silicon. Laser here, just so it shows up in the recording better. So just one slide on each of those modules. So digital logic design and tools. As I said, mini lectures, mini labs. Digital logic starts out with combinational logic, logic gates, composing gates, sequential logic, where we introduce the concept of a clock and sequence the operation of the machine. Pipelined logic, where we're doing deeper computations. We're going to use a few tools. We're going to start out with a tool called Walkwe, which is kind of a drag and drop circuit schematic drawing tool. And then I'll introduce MakerChip, which is where we're going to spend most of our time. MakerChip is my tool out of Redwood EDA. All of these tools are in the browser. So as long as you have your laptop and an internet connection and a browser, you're good to go. We'll talk about the tiny tape-out flow, which takes us to silicon. And we're going to get our hands dirty with field programmable gate arrays, programmable logic. So we have some hardware over there that you can use to program your designs on the physical hardware and blink some LEDs, interact with the real world a little bit. After digital logic, we'll talk about the nature of CPUs and programs, compilers, assemblers, disassemblers. We'll talk about RISC-V and why that's gaining so much attention recently. And talk about its instruction set architecture, which defines the ecosystem for using RISC-V based programs. and we'll talk about the nature of hardware execution of instructions. So this programs and CPUs portion is going to give us a complete view from writing a high-level program down to how the hardware executes that program. I think most likely some of the Module 1 topics are topics that most of this audience has seen before, is reasonably comfortable with. Might feel a little slow, especially day 1 for some of you, but I promise it's going to get really interesting really quickly. So Module 2 focused on actually designing our own RISC-V CPU core. So again, series of mini labs. I'll introduce a concept. Basically, what does this portion of the CPU need to do? This is the logic function you need to implement, and give you a little lab exercise to implement that, and see that behavior that you implemented in simulation. So you're going to start by building a single cycle RISC-V core, a simple core. That'll be a subset of the full RISC-V spec. And then we'll look at improving the performance of that core, getting closer to the nature of core that you might see in the real world in industry with pipelining. And then just completing the CPU. So at this point, the structure of the CPU is in place. We're just adding the detailed definitions of all the instructions in the microarchitecture. And then this is the lecture format portion where we're talking about tools, flows, and methodology, the roles on a design team. So team roles, overview of design tools that are used in the industry, the nature of those tools, the flows and methodologies that have been successful in designing silicon. Different design languages. You're going to be using transaction level Verilog in this workshop. I'll talk a little bit about other options that are out there and the nature of the differences. And we'll look at the detailed tools that we're using and what they are, basically, in this workshop, using Tiny Tapeout. Tiny Tapeout gives you a push-button flow to go from your hardware description to tape-out, which is the process of sending your design off to be fabricated. Yeah? Just a minute, we'll sort this out. Why don't I take this time to hold the room a little bit? It's not so important for the recording anyway. Let me get a sense of what your backgrounds are. So just by show of hands, who has experience with a hardware description language? Verilog, VHDL, anything? So shy. Just put the hand up. It's not that hard. Okay, good. We went from like 2 hands to almost the whole room by just waiting. All right, so a little quicker this time. Let's see, who has experience with RISC-V instruction set architecture? Okay. Let's see, what else is important here? Good? Okay, so that's good. Okay, so I guess we're at the top of this list. So tools, flows, methodology, roles. Roles on a design team. Oh, I guess I did go through. So in this class, we're going to use tiny tape out, which gives us a push button flow, as I said, from your hardware description to the tape out. That all works out of the box. You don't need to look at what's happening, but here we'll take a look under the hood and see what the different tools are doing, just to understand the process. And then I'll talk, at this point you will have used transaction level Verilog a bit, but I'll talk more about the methodology behind it. Actually, it's kind of interesting that you can do a whole RISC-V core and you're really only touching very basic functionality. There's more to the language. And then the rest of the time, however much time we have left, is all dedicated to open project time. I mean, this is what I think is the fun time, right? You've gone through the work of learning all the skills. Here you get to apply those skills in a very open-ended way. Your project, so I think we're... One second. So we're still sorting out the details, but a few of the projects from this workshop will actually be able to tape out on silicon through tiny tape out. So we'll have a little bit of judging, and the winners will get silicon back in several months. So Professor Bopu mentioned this already, but to see it in writing here, approximately, our schedule is to meet here at 9:30, begin promptly at 9:30, have a bit of lecture labs, and then take a break around 11. More lecture labs, more lunch, lecture and labs, 15-minute break, more lecture and labs, pretty straightforward. I'll try to, do a bit of a review at the beginning of each day and a bit of a summary at the end, and we'll stick around afterwards, however long folks have questions and things they want to discuss. Okay, so I guess this is probably a good time to take out the laptops. Once you type out this long URL, you'll have access to everything you need for the course. So this should be the only step where you need to actually type out the URL. From there, you should have links to everything. can see the network. I see. Anyone still working on either the Wi-Fi or the URL? The Wi-Fi is not working, or you can't get the URL right or something, just ask help. Ryan will come over and help out. Anyone still typing? All right, I think we got just about everybody here. So at that repository, mainly it's the README that we care about. So this has the various resources that we'll be using throughout the workshop. We'll get to them. We'll get to them when we get to them. I think now it's probably worth having everybody join the Slack channel that we can use for communication. If you, for some reason, aren't able to attend in person, you have questions. I don't think we'll have to use this too much as long as folks are able to attend in person. But maybe you have a question in the evening or something. It's just good to have a channel of communication. So There's a join link here. Just go ahead and click the join link. That should take you to Slack, where you can log in. And once you've gotten logged in, you go to Slack itself. In any case, if you haven't gotten the login yet, you can always do that later whenever you need to communicate. And then the channel to join is listed here in the slides. The slides should be, and let me make sure the link is correct, should be linked from this repository. I will fix this link. In fact, I'll do that now while you're trying to connect to Slack. So now the README, the first bullet is the slides. if you haven't managed to get into the Slack channel yet, no big deal. Do that anytime. And you can now follow along in the slides as well. So let's continue. So again, starting very basic. I think most of this is old hat for you guys. Let me poll the room again. Let's see. So it seemed like just about everyone has Verilog before. You're obviously comfortable with digital logic. Is anyone new to digital logic? So who I don't like to ask this. I like to ask who has experience, not who doesn't, so you don't have to embarrass yourself. But if you don't embarrass yourself, I'm going to skip some of this. And I don't want people to be lost. So who has not coded hardware description language before? Okay. So I'm going to skip some of this. I'll just blast through it, I guess. So basically, we do as much work as possible in a digital space because digital is well-defined, precise, resilient, reproducible. The analog world is nuanced, imperfect, subject to noise, lossiness, right? So we interacting with the real world is analog. We try to get that analog data into a digital form as quickly as possible so that we can work with it in a more reliable way. I want to make the point that we all sort of jump into this domain and immediately we're talking transistors. Digital logic does not mean transistors, right? Digital logic means you're working with discrete values. Digital logic is also not necessarily binary logic, right? We immediately start talking ones and zeros. Digital doesn't mean binary, it means we're working with discrete values. Binary is when we're using ones and zeros as our compute, right? One of the first computers, the Babbage engine, right? Based on mechanical parts, based on base 10, so that humans could understand it and work with it. So, not transistors, not binary, but this was computing. Computing doesn't mean semiconductors and transistors, right? Digital logic doesn't mean semiconductors and transistors. It could be mechanics like the Babbage engine. It could be vacuum tubes, fluidics, optics, quantum properties, DNA computing, etc. So, as an example, one of my college professors challenged the classroom to create an adding machine out of Legos. And I didn't think much of it at the time, but then I stumbled across someone who had an after-school program for like 5-year-olds. I don't know what age they were. And I said, hey, can I join your class and sit down with your 5-year-olds and play with Legos after school? And he said, sure. So I joined his class and I made this adding machine out of Legos. It was fun. And this is what you get on a grainy camera from the late 90s. So logic gates, I think you're all comfortable with this. Truth tables, simplest NOT gate. Input 0, output is 1. Input's 1, output is 0. AND function is going to be 1 only if both inputs are 1. And then inversions of AND or exclusive or, you put a bubble on the output, the symbol, and the output's the inverse. So if we compare the AND output to the NAND output, they're opposite each other. Exclusive or asserted at the output if one but not both inputs are asserted. I think everyone's probably comfortable with that. And this is just the concept of composing those basic building block logic gates, right? This circuit happens to be a full adder, doesn't really matter at this point, but bits come in, wires take the signals to gates, gates produce values and those propagate. Right, so we can throw values at the inputs and they'll propagate through and stabilize on output values. Everyone comfortable with binary? you don't raise your hand, I'm going to go over it. So, okay. Adding in binary, same as decimal, but you only have 2 digits to work with. So the circuit that we were looking at, the full adder, right, that happens to be one that computes the addition of 2 bits, and you can chain them together to do computation of multi-bit numbers. So the first tool that we're going to play around with online is called NAND Game. So go ahead to nandgame.com. I'm going to do the same myself. So certain of the logic gates are, I believe the term is universal logic gates. Somebody can correct me if I'm wrong, okay. So a universal logic gate is one that can be composed to create any other logic gate. NAND happens to be one of them, and this game is an opportunity to kind of explore that. We'll first build an AND gate, and then use that AND gate, compose that AND gate to build other logic functions. So it's just kind of a warm-up exercise to get comfortable with the basic building blocks of digital logic. So I think there's some terms to accept. They're very lengthy and verbose, and say there's no reason you shouldn't accept this. So I'm going to say just accept it. I think actually I haven't been here before. I thought there was a long, lengthy thing we talked about. In any case, if it does, accept it. On the right here, you've got a description of the first, I guess, the overall game. And then a description here of what your task is for this one. I don't actually find value in this exercise. Most of you probably have the background to understand that here we're trying to build a NAND gate out of relays, but forget about this first exercise. I'm just going to use this as a demonstration of how to interact with this tool. So you can drag the components into place. If I remember right from several months ago, the solution to this, pick it up this way. So click the destination of the signal, the little triangle, and drag it to where you want it hooked up. So just follow along with me to get comfortable. You can play around with the inputs here, so I can switch the inputs this way from 0 to 1, and you can see the effect that has on the output, right? So you can play around with it, make sure it's behaving the way you expect it to. And when you think you're good to go, you can check solution. Looks like I remembered correctly. So I'll give you just a second to get that hooked up. We get it, next level. So this exercise now is to use that NAND component that you created. Now you get that as a basic building block, and connect up a circuit that will implement an inverter function. So basically, I'll give you 5 or 10 minutes to just play around with all these exercises, go through them at your own pace, get progressively more and more interesting. It doesn't really matter how far you get. This will just be time-based. I'll give you so much time. You can always come back here and play around with the later exercises. They are fun. A lot of my mission is to make circuit design just more fun. This is not my site, but I think they did a really nice job of making it approachable and fun exercise, gamifying it, not making it scary like the industry tends to do. It's the same for everybody. I think these are all sort of canned exercises. They'll have you build up an adder circuit, I think. I don't remember how far they go. I think I gave up at some point. If you need help, just raise your hand. All right, so let's talk a little bit about tiny tape out, the nature of tiny tape out. So this is not tiny tape out specifically. This is chip ignite from eFabless. So eFabless offers this this easy path to silicon. Right? So eFabless gives you this Caravelle harness, and your design goes into the empty box there. And then they give you a path to fabricating that silicon and mounting it so that you can play around with it. So this is the picture for chip ignite from eFabless. Right? They give you this framework to work in. Right? Down here in Caravelle, this is a control processor to help bring up your hardware, whatever it may be. And they provide this multi-project wafer framework. So they combine your project with 39 other projects, put that onto a mask, and stamp it out on the wafer. So the process of fabricating silicon, right, wafer lithography, you build the masks, right? So in this case, the 40 projects, you have a light source that goes through a lens. The light gets passed through this mask that you create, gets focused by another lens, and the light affects the properties of the silicon. You do that through a series of steps and carve out the layers of your silicon. So on top of chip ignite, so chip ignite brings the price point down to about $10,000 for a project. Independent of eFabless, another guy, Matt Ben primarily, looked at that and said, that's really cool, it's a neat concept, why don't we take that a step further? So let's take what eFabless provides and slice that up into 500 units and give you access to individual units. You can do a project that's just a single tile, or you can do a project that's multiple tiles. So they'll collect up projects filling up 500 tiles, and that will be one of the chip ignite projects. And then that gets fabricated, mounted on the board, and sent to you. So when you get your board back or your chip back, that's got your project, and it's got all the other projects that have been squeezed onto here. And then they have some software infrastructure to select amongst those projects, so you can select your project and play around with it. So the infrastructure here is a bunch of routing wires and muxes to connect up the ins and outs of this project to your project when it's configured for your project, or configure them to connect up to anybody else's project. You can play around with any project that's on the silicon. Okay, so this is the actual chip ignite chip as it would be delivered to you. So this is showing both ASIC flow on the left and field programmable gate array flow on the right. Anybody not familiar with FPGAs? Okay, a couple. And then 6 or 7 of you that are afraid to raise your hand as well. So an ASIC is what's running in your laptops. An FPGA is programmable logic. So it's got a sea of logic sprinkled down. It's got an interconnect of routing that you can configure to connect those gates. So all the gates are there. My first internship was with Eastman Kodak. Doesn't exist anymore because they thought analog was the future. But the room that they sat me in to do my work had this big box in the corner, and once in a while it would start clicking and clacking. Right? It was doing the same thing an FPGA does, but physically. It had relays to configure the connections and whatever hardware components. So it was a lot more fun with all the clicking and clacking than an FPGA that's perfectly silent. But I'm sure that unit costs a lot more than the FPGAs, so you're stuck with the FPGAs. So either way, the process starts from your HDL code, which is describing the hardware description language, describing the circuit, the behavior that you want to implement. For an ASIC flow, that gets compiled into, generally we use cell-based design, so a bunch of standard cells with different logic functions all laid out any way you'd like them to be, because you're producing the silicon in a custom way. Or in the FPGA, you're producing configurations, okay, and that's known as a bit stream, which specifies all the bits that control the individual logic functions, as well as the connections of all the routing to connect up those logic functions. So, the hardware is laid out in a fixed way. You're controlling the settings of these bits that generate that bit stream, and download it onto the FPGA to configure the FPGA for your particular logic function. Right? So the FPGA itself is an ASIC. Some other company went through this ASIC flow to create the FPGA chip, and now you have this flow to configure that chip. Right, so of course, the ASIC flow can be easily many millions of dollars and take many months. The FPGA flow, once you have the FPGA chip in hand, it's a minute turnaround or something. Of course, you're giving up something, right? You don't have the flexibility with the FPGA that you have with the ASIC to optimize the circuitry. So you might lose about 10% in area, 10% in power, 10% in, 10x power. Sorry, not lose. You might, 10x. So 10x area, 10x power, 10x performance, kind of the ballpark. Just a view of, next level down of what's in the FPGA chip. And I think depending on time, Dr. Bofu's got additional material on FPGAs. But I'll go this far, and we'll see how time permits. But generally, most FPGA parts look pretty similarly like this picture. You'll certainly see variations, but generally they look like this, where there are a sea of logic functions. Right? So that's these little boxes, and interconnect with programmable interconnect, right? So at the intersection of the crossing wires, you can basically short the wires out and use that to create routing throughout the chip. And then you've got these larger blocks that are small memories, small RAMs, block RAM. And around the periphery, you've got I/O components, and then also this thinner one here in this diagram is representing DSP blocks, which are basically an add multiply unit. Just because add multiply is a very common operation, so they give you a highly optimized add multiply unit. And you'll see other variations of FPGAs, right? You might see FPGAs that have hard cores on them, CPU cores, and other higher order logic functions that may be of value. You might see integrated analog circuitry as well in certain FPGAs. In ASIC, you get to design everything yourself, at least on the grid. This is a picture from Tiny Tape Out. Okay, so I don't actually know the tool here. It's probably the tool itself that's representing this is probably used by Tiny Tape Out. I don't think they created it. Could be wrong. I don't know. But this is a representation of a Tiny Tape Out design. So we'll play around with this tool later, but you know, you can see the high-level metals, lower-level metals, and logic underneath that. With tiny tape out, we're basically producing logic functions that, let me turn on my laser pointer, logic functions that are going to be built into this along with the 500 other tiles. And in this class, I have a bunch of boards over here. Should be enough for each table to have their own board, which is FPGA based. All right, so the designs that you create to be taped out and manufactured and turned into an ASIC, you can also run those same designs in an FPGA using this FPGA carrier board. Right, so the carrier board sits on top, and the tiny tape out board is underneath. So other than being on FPGA versus ASIC and therefore running a little bit slower, you can do the same logic function. It works out quite nicely because the FPGA logic will be larger and take more area, but in the FPGA case, it's just your project that you're putting on the FPGA, right? Whereas in the ASIC case, you're squeezing your logic with a whole bunch of other projects. So, you know, generally, if your logic is going to work in the ASIC flow, it'll fit in the FPGA without any issue. The next online tool we're going to play around with is Walkwe. So this is something that the Tiny Tape Out folks put together. So you can go ahead and open up https tinytapeout.com and go through these steps. So this also similar to the NAND game is a drag and drop kind of environment for constructing your logic. It's got a template here for specifically for Tiny Tape Out. So I'll do this as well. So tinytapeout.com, digital design guide here. Getting started with our design tools, the first link, and then scrolling down the Walkwe template. Okay, so the README on the left, we can shrink that down. So you can use the mouse to drag and drop the screen. You can click on components here, drag them around. As you drag the component, release, it's going to connect up the wires. So what we have here, this block represents the inputs of our Tiny Tape Out. Now kind of all over the place. The Tiny Tape Out board has 8 input wires and 8 output wires. The boards that we have are an older generation Tiny Tape Out board. They just have those 8 inputs and 8 outputs. The newer boards also have 8 bidirectional I/O pins. So those are the ones down here. So those of you who do get to tape out and get an ASIC back, that will support the bidirectionals, but the FPGA boards that we had to play around with just have the unidirectional 8 in, 8 out. Therefore, it's going to be easier for us to just work with the ins and outs. But if you really need the bidirectionals for some reason when you get your ASIC, even though we can't test them with the FPGA, you could potentially use those. Let's see, what else about this framework? So maybe I should take out one of the boards, or maybe any of them. Professor Roach, maybe pass it around. We're at the bottom, that's other stuff. Yeah. So these boards are loose in here, so may as well, I don't know, just take out a couple and pass them around, I guess. We'll use them today, so. Yeah, maybe pass 2 or 3 around the class. I'll take them myself too. So Professor Root's going to pass some boards around. This is the actual tiny tape-out board. You saw the picture in the slide. But basically, you've got the 8 input pins over here on this board. And again, this looks different than the board that you'll get back if you do tape-out. But on this one, you've got 8 inputs that you can switch. And the 8 outputs are connected up to the 7-segment display here. Okay. And you're seeing the 7-segment display represented in Walkly. All right. So also in Walkly, basically the other logic here is representing the reset and the clock that are controlling your circuit. So we're sort of in design mode, right, where you can interact with the components and move them around. So in this mode, I can hit the plus and find components from this long library of components and add them to my circuit. So I could drop an LED over here. Let me try that again. So I think just click on the component in the library and it'll drop down in the upper corner. You can drag it. You could color wires just to help yourself keep track of things. How did I lose that? I'm not sure how I made that pop up. So basically, you'd work with the LEDs to understand the values. The only way to see values on the wires is to actually connect them up to an LED. So for example, and I forget which way is which, so I might get this wrong. But I'll hook up this LED to output 1. And I'm going to need a ground as well. So here's a ground component. I should be able to, let's see, copy paste. Okay, so Control C, Control V, copy paste. I got myself a new ground. And I can connect these up. So this is design mode. You can switch to simulation mode with the play button. So I'll hit play. Simulation is free running. Okay, so you can see the stopwatch here, and it's just going to keep running. Let's see if I did this right. So, all right. So this output should be high. I'm guessing I hooked these up backwards. So let's stop this. Select the wire. Backspace to delete. Try hooking that up the other way around. Okay, so now you can see the LED is lit up because this output 1 value is 1. So for the LEDs, you'll hook up ground on the left and the signal you want to monitor on the right. What else to mention here? So while I'm simulating, the input buttons, you can switch. Okay. The LED segments are hooked up to the outputs. You can you can see here, since you have physical wires with the hookup, what's hooked up to what. But the top segment here is output 0, output 1, 2, 3, I'm going my laser pointer. I guess I can't here. 4, 5, 6, and 7 is the decimal point. So the wiring that's hooked up in the template, that is how it's hooked up on the board. That's not something you can physically change on the real board, so leave that as it is. But our exercise now is going to be to stop the simulation. If you shift and drag, you can select multiple components. I'm going to delete the logic that's in here. Delete the wires. So let's start off fresh. I'm gonna actually, I think in my slides, actually have you hook up some LEDs first. So so this we went over. So the first thing I'll have you do is just hook up some LEDs on the output. And I guess we do get into tiny tape out now. I was thinking that came later. So maybe you could pass out boards to everybody. I think they're going to need them. All right. So the first exercise is to hook up some LEDs. I think when we went through this before, we might have had some issue with deleting the actual 7-segment display. So leave the 7-segment display in place, but see if you can hook up some LEDs to these 3 outputs. Play around with the input switches like I did. Just blink the LEDs just as a warm-up exercise. Any questions about that, this exercise? Yeah. Yeah, so the design that you do here, everything between the inputs and the outputs is the logic that will go on to tiny tape out. For the design environment here, this is Walkwe. So I think Walkwe comes out of the Arduino ecosystem or something, but it's been used to apply here to tiny tape out. So basically the tiny tape out folks made a library of components that's appropriate for tiny tape out. Yeah, so what we're going to be able to do is, design something simple in Walkwe and go through the tiny tape out flow with your Walkwe design, and then play around with that design on the FPGA boards. Okay, so the bulk of this class will use text-based coding, hardware description language, but several minutes we'll use this drag and drop with Walkwe to make some logic for the FPGA board. So first I'll hook up my wires again. I've got my first LED. So I will copy paste. It looks like I'm having similar problems to other students. Doesn't look like my lights are connected. Oh, okay. I see my problem. I don't know if this was your problem as well. Yeah, the first two are clock and reset. So I hooked these up to the wrong wires. This is 0 to 0. To 1. All right, are we generally okay? So let's move on to the next one. So the exercise here is just to make a circuit that's a little bit more interesting than just some wires. So we'll do a tiny little adder circuit, right? So these are our full adders. You can just refer to the logic function. So find the corresponding gates in the library. So again, in design mode, the plus will give you your library. You can type in, if you need an XOR gate, you can type in XOR and grab that gate. So use that to build up this circuit. Right? This circuit is going to go between the inputs and the outputs. So hook up your inputs however you choose, and likewise hook up your outputs however you choose. You've got, we'll do it, so with two full adders like this is a 2-bit add, right? You've got your two input bits for your first source, your first add end, that's A0 and A1, and then B0 and B1 are your second input value, so each 2 bits. This will add them together and produce the value S, the sum. S0 and S1 are those bits, right? So the zeros are the low order bit, and the ones are the high order bit. Yeah, so the low order bits are worth 1, the high order bits are worth 2 binary. And then you also have your carry output. So basically open up space between these. You probably want to select, so shift, select all of this stuff on the right and just move it over to free up some space in the middle, because this will get messy. And then go ahead and try to implement this. And then see in simulation, right? Toggle the inputs, see that the outputs are indeed producing an add function. You can take advantage of the fact that your LEDs are hooked up to understand the outputs, or the 7-segment display is also hooked up, right? So again, it's output 0 at the top, and then kind of going around clockwise. 0, 1, 2, 3, 4, 5. That's all you need to hook up. All right. One thing I forgot from the last lab is to actually save the project. So I think it auto-saves if I remember right. Can't remember for sure. But save a copy. Give it a name. Make it public. I don't know if all this works if it's unlisted. I think it should, but just make it public. Save. Project saving failed. Okay, I'm not signed in. Okay, sign in. Once you save, you get an ID number at the top for your project, and you can return to that URL. You should also, I forget how to do this, be able to see your projects. Here it is, my projects. Blazing speed. Okay, so I don't know why these aren't loading, but I don't have the patience to wait any longer, so I should be able to click on my GIAN project, load it back in. Okay, so again, I think it auto-saves, but I'm not entirely I might be wrong about that. But let's make a change. Okay, so once I make a change, save is an option. So make sure you're saving your work as you go. Okay, so let's start up again. Everybody good with your designs? Working in simulation? Any problems? Okay, so the next step is to actually take the designs that you created and get them onto the FPGA demo board. So if you go to the GitLab repository, there's a link here for instructions for programming your FPGA and take out your ASIC. So go ahead to that and open it up. And actually, unlike what I just did, it would be a good idea to control-click that to open it in a new tab, because we're going to need to refer to the repository again. Maybe I'll full screen this. So I guess the first part of this I'll walk through with you. And then there's some software installation to actually use the USB to program your boards. That's specific to your particular platform, whether you're Windows or Linux or Mac. So I'm going to let you read that part. But the first part here, if you bear with me, struggling through these steps, is to set up your Git repositories. So who does not have a GitHub account currently? Okay, so most of you do, but not everyone. You'll need one. So go to github.com, and it's going to look different for me since I do have an account. And I'm logged into that account. But it will present you with create an account instructions, just like anywhere. GitHub does require two-factor authentication now. So the setup for it is a little bit more tedious, but I'll give you some time to just work through that. Others who have a GitHub account maybe can help you speed through it. And I think I should just give folks a little bit of time to get everybody on the same page, because if I race ahead before you've got an account, it's going to be difficult. So if you're all set up, maybe you can help somebody else out. So if you're still working on getting your account set up, you can pair with somebody else and work together with them. And then when you do have more time, create your account. And at that point, you can go through these instructions, and get caught up. So how many people are still struggling with their accounts? Oh, okay. Are you close? Or having trouble? Okay, so partner up with the other two at the table. Okay, so the next step here, there's 3 repositories that we're going to use throughout the course. And we'll set up all 3 now. It's the same steps for each one. So with the instructions opened up, probably, yeah, just click. So click on the first one. Okay, so we need to use this repository as a template. So under use this template, create a new repository. And do these side by side. So creating a new repository from this template, you'll give it a repository name. Give it a description that's more meaningful than the one I'm giving it. We might have to do these as public, so just leave it public. And then create repository. So these instructions shouldn't actually say fork. Technically, it's not a fork. But create a new repository, we just did. So you may or may not be prompted. I don't think you will be, but if you are, we want to enable workflows. And just to make sure that things are set up right, go to the actions. And you should see that we've got these 3 builds actively running, these 3 workflows. If anybody does not have these running, let me know. All good? Yeah, that might be expected. Is everybody good? Seems a mix. Okay. So once you confirm that the workflows are running, we also need to enable GitHub pages. And those steps are here. Go to Settings. Settings. Select Pages here. And change source should be deployed from branch, so we want to change that to GitHub Actions. Okay, so all we're doing there is enabling GitHub Pages, which is enabling the workflows that get kicked off automatically by GitHub to generate web pages. And the tiny tape out flow does that for us. So we need to enable it. This picture shows those 3 steps if you missed it. settings, pages, GitHub Actions. Okay, and after you've got that repository set up, there are 2 more repositories to do the same steps. Don't think I'll need to do those myself. So I'll just let you step through the instructions on your own. Well, maybe I'll go through and do it. Template, create new. What do I create? Is running. Settings. Pages. Actions. So I think this third repository, you know what? Don't bother with the third repository yet. This is for our final submission. Tiny Tapeout 10 has already gone. Every new Tiny Tapeout, they create another repository specific for that tapeout. I don't like the way they do it, but anyway, that's what they do. The Tiny Tapeout 11, which is what we'll be using, submission repository is not yet created. So that's not available yet. So we'll just do the setup for the first 2. Everybody all set with those 2? Okay, so I'll just give you a couple minutes to go through the steps. So we'll use that first repository, the Walkwe repository, to connect with the projects that you just created in Walkwe. Okay. So the steps for doing that are here. We want to update the repository that you just created a copy of to contain that ID. So let's see, for me, which the template inside Walkwe? They're wondering about the repository and what that does. Yeah, so the repository that we just copied provides the whole workflow to take you from your Walkwe design all the way onto the FPGA or even the ASIC. Okay. So right now we're just going to use that as a push-button flow. We're going to connect it to your project. It's going to build. It's going to create the FPGA bit stream. We're going to load that on that FPGA demo board. Later we'll walk through in more detail what are all the steps that get us there. But for now, we just want to get the design that you created in Walkwe onto the FPGA. So here's my copy of the Walkwe repository. So I need to go, what is this about? To the top level of the repository, and there should be, I think it's the info.yaml. Yeah, info.yaml. At the top of the info.yaml, you see this Walkwe project ID. What is this? We want to edit this ID, so edit the file. There's this little pencil icon here. So click on the pencil for info.yaml. Now we're editing the file, and we need to drop in the ID for our project. So if you go back to where is my Walkwe project? Here, right? Make sure your project is saved. So make sure the save is gray, indicating that there's nothing to save. And then copy your project ID. And paste it here. And then commit your change. So everybody can do that step. Once you do that, take a look under Actions. So every time you commit a change to your GitHub repository, that's going to kick off the workflow again, the actions. And they're going to run 3 different workflows. And we'll take a look at what those are doing in a minute. But I just want to give you time to all make that edit. So I know at least one student, the the DFU utils install using option B. Option A should work. Chrome was blocking the download, so you have to give it permission. So Srinivas, what were students stuck on? Okay. So I'm going to click option A here for the zip. Click this one. Suspicious download blocked. Okay. So that should have given me a download folder here. I'm going to open up the folder. Extract all. Okay, so this is what I downloaded and extracted. I put this in a folder called Win64. There's also a Win64 folder within the content that was extracted, and that has DFU utils. DFU util, which is the executable. So let's get everybody that far, and then we'll try to run it. Yeah, so let me make sure everybody gets this. Who's got DFU util successfully? Downloaded, accessible. Yeah, this is it. It's just the DFU utils application. Okay. So the next step is to program the FPGA using DFU util. Again, the instructions are particular to your, well, okay, less specific to your platform, I guess. So where do I describe that? Okay. So to actually do the download, okay, so there's a little button on the carrier board, the top board, labeled boot. It's this little button right here. You need to hold that button down when you plug in your USB cable. There are two USB-C connections here. There's one on the main board and there's one on the carrier board. We're just interacting with the carrier board that has the FPGA on it. So you want to hold down boot. If your USB cable plugged into your PC, plug in to the USB-C connector here, and after it's plugged in, release the boot button. Okay, so that puts the FPGA board in this DFU mode. It's ready for a download. Does anybody need a different type of USB cable? Is everybody okay with the cables we have? So everybody has a USB-A on their laptop? All right. Okay, so once you've got that, you've got your FPGA board in DFU mode. Then we want to run the DFU util program, give in your bit stream file, and that will upload the bit stream to the FPGA. Okay, so open a command window or a terminal. DFU-util, and we need the path to that, which I think for me is win. Yeah, you're right, I could do that. So for me, my download is here. This should have DFU-util exe. So I'll do DFU-util, and first thing we want to do is -L. That's going to tell us the devices that we have. I didn't actually plug in here. So can you grab me one of the cables? So if you have your device plugged in, you should see the devices listed. So again, I'm going to put my board in DFU-util mode, press the boot button, plug in the USB-C release. It should be ready for a download. And then DFU-util-L should tell me that it's connected. I see two devices here, USB devices. The one is for the bit stream, and the one is for FPGA, for RISC-V firmware. Okay, we're going to just do the bit stream. So the RISC-V firmware one is for programming the CPU that's part of the, well, we don't have Parabel. Actually, I don't know. Never mind. But we're using the ICE40 bit stream. You should notice that for the ICE40 bit stream device, that it's Alt 0. And the next, so this just confirms that we're actually connected. The command to actually do the download is this one. So DFU-util-R-A. This is the alt number for the device, which for us is 0. Again, because of this Alt 0 here. -D for download, I believe, and then the path to the bit stream. Remember where it is. Bitstream locked it in. DFU-util-R-A-0-D. Downloads, it's Walkley. So once you get all the paths correct for that command, looks like my download succeeded. I got a pop-up saying the device is not recognized. It happens. I'm not too worried about it. I don't know why, but so I think my device is programmed correctly. It seems to be behaving correctly. If you had any trouble, let me know.
हेलो हेलो अभी हो गया हेलो हेलो 1 2 3 हेलो हेलो 1 2 3 हेलो 1 2 3